Material-based plastic are still widely used, but they cause serious environmental problems, such as long degradation time and plastic waste accumulation. Because of this, natural polymers such as starch and cellulose are gaining attention since they are biodegradable and renewable. However, these materials usually have weaker mechanical properties and are sensitive to moisture. So, polymer blending, such as starch blended with polyvinyl alcohol or PVA, is used to improve material performance through hydrogen bonding interactions. At the same time, extracting cellulose from cocoa pod husk is an example of agricultural waste valorization and supports a circular economy. Therefore, in this study, SCM-EDX and FTIR are used to compare the morphology, elemental composition, and functional groups of starch PVA film and extracted cellulose. For this project, there are three main objectives. First, to compare two materials with different chemical nature, which are starch PVA film as semi-synthetic polymer and cellulose extracted from cocoa pod husk as a natural polymer. Second, to characterize the surface morphology and elemental composition of both samples using SCM-EDX. And third, to identify and analyze the functional group in this material using FTIR. For the preparation of the starch PVA film, the reagents used were PVA powder, starch powder, glycerol, and distilled water. The apparatus include beakers, a measuring cylinder, analytical balance, magnetic stirrer, hot plate, thermometer, petri dish, and an oven. First, 100 milliliters of distilled water was heated to 97 degrees Celsius. Then, 3.5 grams of PVA powder was slowly added and stirred for 30 minutes until a clear solution was formed. Secondly, 1.5 grams of starch powder was added into the PVA solution and heated again for another 30 minutes to ensure complete gelatinization. Thirdly, 2 milliliters of glycerol was added as a plasticizer and stirred for 15 minutes. About 5 grams of the polymer solution then poured into a petri dish and spread evenly. Finally, the film was dried in an oven at 45 degrees Celsius for 8 hours, cooled to room temperature, and once the starch PVA film was prepared, it was sent for FTIR analysis to identify the functional groups present. SCM-EDX analysis was also carried out to examine the surface morphology and elemental composition of the film. For the extraction of cellulose from cocoa pod husk, several reagents and apparatus were used. These include cocoa pod husk powder, sodium hydroxide solution, distilled water, and ethanol. The apparatus involved include beakers, a measuring cylinder, analytical balance, magnetic stirrer, hot plate, filter paper, filter funder, and an Firstly, the dry cocoa pod husk was cut into smaller pieces and ground into fine powder to increase surface area. Secondly, the powder was treated with 12% sodium hydroxide solution for 24 hours to remove non-cellulosic components. Thirdly, the residue was rinsed thoroughly with distilled water until a neutral pH was reached. Finally, the sample was washed with 95% ethanol to remove impurities and then oven dried at 60 degrees Celsius until a constant weight was obtained. After drying, the extracted cellulose was sent for FTIR analysis to identify the functional groups present. In addition, SCM and EDX analysis were conducted to observe the surface morphology and to determine the elemental composition of the cellulose sample.
At 100 magnification, the film surface is smooth and continuous with only a few cracks or wrinkles. This indicates successful film preparation and good macroscopic uniformity. When the magnification is increased to 500, slight surface roundness and minor irregularity can be observed. This indicates that the stuff is well dispersed in the PVA matrix. At 5000 magnification, finer surface textures such as small bud and shallow dispersion can be observed. This indicates that starch is partially integrated and gelatinized in the PVA network. At the 10,000 magnification, the film exhibits a dense and compact structure without visible pore and micro cracks. This dense morphology confirms strong intermolecular interaction and effective hydrogen bonding, thereby enhance the structural integrity of the film. The elemental composition of the PVA starch film was analyzed by using the EDX. The results show that carbon and oxygen are dominant elements, with carbon accounting for approximately 53.6% by mass and oxygen about 46.2%. This element originate from the polymer backbone of the PVA and the polysaccharide chains of the starch, which confirming the organic nature of the film. A very small amount of the sodium was also detected, which may be due to the residue sought from the starch preparation process. However, its concentration can be ignored and it does not affect the overall structure of the film. Overall, the EDX result confirmed that the film consists mainly of the carbon and oxygen-rich biodegradable. Lastly, the FTIR analysis was performed to identify the functional group present in the PVA starch film. A broad absorption band at 3274 wavelength corresponds to the OH stretching, which indicates the hydrogen bonding between the PVA and starch hydroxyl group. The peak at 2928 wavelength represents the CH stretching from the PVA backbone and confirm the presence of the synthetic polymer component. The peak at 1145 wavelength corresponds to the COC stretching, indicate the presence of the glycosidic bond from the starch. And then the 1078 wavelength represents the CO stretching from the both polymer and confirming the good molecular blending. In summary, the FTIR result confirmed the strong intermolecular interaction and good compatibility between the PVA and starch in the film.
Now, we look at the morphological characterization of the PVA starch composite film using scanning electron microscopy or SEM. SEM analysis was conducted at multiple magnification such as 100 magnification, 500 magnification, 5000 magnification, and 10,000 magnification. The reason for using different magnification is to examine the film structure across various length scales, allowing us to observe both macroscopic features like overall uniformity and microscopic features such as surface texture and fine detail. At low magnification, the film structure appears smooth and continuous, with no major crack or void. This indicates that the solution casting method successfully produced a uniform film. The absence of phase separation also suggests strong compatibility between starch and PVA, meaning the two polymers are well mixed at the macroscopic level. At higher magnifications, we observe a fine surface texture, including shallow depression and evenly distributed microbumps. These features are attributed to gelatinous starch granule embedded within the PVA matrix. At 10,000 magnification, the morphology appears dense and compact, highlighting strong intermolecular interaction within the composite. So, from a chemistry perspective, the dense morphology indicates strong hydrogen bonding between starch and PVA change. This results in improved structural cohesion, reduced brittleness, and enhanced mechanical flexibility compared to pure starch films, which are typically fragile. Blending starch with PVA effectively overcomes the structural limitation of starch alone. So, in summary, SEM analysis confirmed that PVA starch blend form a well-integrated semi-polymer film with improved film forming ability and mechanical performance. The morphology observed at low and high magnifications clearly support the enhanced property of the composite film. Moving on, we perform elemental analysis of the PVA starch composite film using energy dispersive X-ray spectroscopy or EDX. The main goal was to determine the elemental composition of the film. The analysis showed that carbon and oxygen are the dominant element, contributing 53.59% and 46.24% by weight, respectively. This is consistent with the chemical structure of starch and PVA, both of which contain carbon backbone and abundant hydroxyl group. The high oxygen content is particularly important because it indicates many hydroxyl groups which facilitate extensive hydrogen bonding. This hydrogen bonding enhances polymer compatibility and film cohesion, supporting the structural integrity observed in SEM analysis. Additionally, a trace amount of sodium, only 0.17% by weight, was detected. This is likely a minor residue from starch processing and does not significantly affect the polymer properties. Overall, EDX confirmed that the PVA starch composite is a clean, organic, and biodegradable polymer blend with minimal inorganic contamination, reinforcing the reliability of our film preparation method. Next, we perform Fourier transform infrared spectroscopy, or FTIR, to investigate the functional group and molecular interaction within the PVA starch composite film. What we can observe is that a broad OH peak at 3274 indicates extensive hydrogen bonding between starch and PVA change. This strong intermolecular interaction enhances film cohesion. Next, the CH stretching peak at 2928 confirms the presence of PVA backbone. CH2 bending vibration at 1418 and 133 correspond to the semi-crystalline region of PVA, which contributes to structural rigidity. Peak between 1145 to 1078 correspond to COC and CO stretching, reflecting starch glycosidic linkage and alcohol group from PVA. Glucose ring vibration from 997 to 760 confirm that the starch structure remains intact within the composite. So what we can interpret from this result is that the FTIR result confirms that starch and PVA interact primarily through hydrogen bonding with no covalent bond formation detected. This is significant because it enhances mechanical flexibility while maintaining film cohesion. Semi-crystalline PVA region adds structural stability, and the intact starch structure ensures the biodegradability of the composite film. So, overall, FTIR confirmed that the PVA starch composite film has strong intermolecular interaction, preserves starch integrity, and suitable chemical characteristics for sustainable material application. Finally, let's discuss the limitation, improvement, and potential application of the PVA starch composite film. So first, let me look at the limitation of PVA starch composite film. The film is hydrophilic due to abundant hydroxyl group, making it sensitive to moisture and water uptake. Next, it is not suitable for application requiring high water resistance without further modification. And lastly, its mechanical strength is sufficient for moderate load but not for heavy-duty application. So, what is the potential improvement that we can do to overcome this limitation? So, to overcome this limitation, several strategies can be employed, such as, first, surface treatment to enhance water resistance, second, chemical modification or cross-linking to improve stability, and lastly, barrier coating to reduce moisture absorption. So, despite its limitation, the starch or PVA composite film is suitable for short-term and disposed use due to its good flexibility, moderate mechanical strength, and biodegradability, such as biodegradable packaging film, environment-friendly wrapping material, protective coating for short-term use. The incorporation of glycerol as a plasticizer further improves toughness and elongation, enhancing flexibility for this application. Next, with additional modification, the film could be used in more specialized applications such as, first, absorption system, utilizing the hydrophilic functional group, second, biomedical material, and third, control release station. So, potential enhancement for this application include moisture-resistant coating, cross-linking, and surface functionalization for target performance. So, in a summary, the PVA starch composite film demonstrates a balance between sustainability and functionality. Its property makes it ideal for eco-friendly short-term application, while further modification could expand its use to advanced and specialized application, maintaining its biodegradability and mechanical.
Next, moving on to the result of the 𝐏𝐭 cellulose. The SEM image at increasing magnification show progressive morphological change in the alkali-treated cellulose. At 100 magnification, the surface appears irregular and heterogeneous, representing the bulk fiber structure of the 𝐏𝐭, while at the 500 magnification, the surface roughness and groove become more apparent, indicating partial removal of lignin and hemicellulose. Meanwhile, at higher magnification of 5000 and 10,000, elongated fibrillar bundles and microfibril aggregates are observed, confirming the exposure of cellulose fibers after alkaline treatment. On to the ADX analysis. Based on the ADX spectrum here, carbon and oxygen are the dominant elements, which is consistent with the chemical composition of the cellulose. The elemental mapping further shows a uniform distribution of carbon and oxygen across the analyzed area, indicating a homogeneous cellulose structure. Trace amounts of sodium and calcium are also detected, which may originate from the alkaline treatment process and naturally occurring minerals in the cocoa. The FTR analysis. The broad absorption band around 3,241 per centimeter correspond to OH stretching, indicating abundant hydroxyl group and extensive hydrogen bonding in cellulose. The CH stretching band near 2,900 per centimeter represent the polysaccharide backbone of cellulose, and they have weak peak around 1,555 per centimeter, suggests that most of lignin and hemicellulose were removed during alkaline treatment. Additionally, the band at 1,422 per centimeter indicates the preservation of the non-cellulose one crystalline structure, while strong peaks between 1,050 and 1,070 per centimeter correspond to CO stretching vibration in cellulose. Finally, the presence of the beta-glycosidic linkage peak at approximately 878 per centimeter confirm the characteristic of the beta-1,4 structure of cellulose.
The SEM analysis. SEM was used to observe the surface morphology and the structural change of the fibers after the alkaline treatments. And at lower magnifications, the cellulose surface appear rough and heterogeneous, which is typical of the lignocellulosic biomass that have undergone the chemical treatment. At higher magnification, such as 5,000 and 10,000, elongated and more distinct cellulose fibers can be observed, along with the pores, cracks, and surface groove. These features indicate that the alkaline treatments partially remove lignin and hemicellulose from the cocoa pod husk structure. These morphological changes occur because the sodium hydroxide penetrates the plant cell wall and cleaves the ester and ether linkage between the lignin and hemicellulose and also cellulose. As a result, the structural matrix is weakened, reducing the so-called gluing effect of the non-cellulosic components and allowing cellulose fibers to partially separate, a process known as defibrillation. The increased surface of roughness and formations of fissures lead to the highest surface area, which is beneficial from a materials perspective because it improves the mechanical interlocking and the interfacial adhesions when cellulose is used as a reinforcing
Starting with
material.
PTX analysis, this technique was used to identify the elemental compositions of the extracted cellulose. The result shows that carbon and oxygen are the dominant elements detected, which is consistent with the chemical structures of cellulose as a polysaccharide compound, mainly of carbon, hydrogen, and oxygen. This confirms that the extraction process successfully enriched the cellulose fractions from the cocoa pod husk. Only minimal amounts of other elements were detected, indicating a limited inorganic contamination. Any trace of sodium presence is most likely due to residual sodium hydroxide used during the alkaline treatment, highlighting the importance of proper washing step after the extraction.
The FTR spectroscopy was used to identify the functional groups and confirm the chemical structures of the extracted cellulose. So the bulk absorption bands around 3,241 cm per cube correspond to the OH stretching vibrations, indicating the extensive hydrogen bonding among the hydroxyl groups, which is a characteristic feature of cellulose. The CH stretching band bonds near the 2,900 confirm the polysaccharide backbone of the cellulose. A weak peak is observed around 1,555, is attributed to the carbonyl and aromatic structures from the residual lignin and hemicellulose. The reduced intensity of the lignin-related peak occurs because the alkaline treatment saponifies the ester bonds and disrupts the aromatic lignin structures. However, without a bleaching step, some lignin and hemicellulose remain in the materials. The absorption bands around 1,422 indicates that the intentions of cellulose 1's crystalline structures, showing that the cellulose backbone is preserved during treatment. Strong peaks in the regions of the 1,050 to 1,017 together with the beta-1,4-glycosidic linkage peak around 878 further confirm the presence of the cellulose. However, SEM image still show the presence of fiber bundles, and the FTIR analysis detects weak lignins and hemicellulose-related peaks. This indicates that the alkaline treatment alone is not sufficient for complete delignification, mainly because no bleaching step was applied during the experiments. So to improve the results, hydrogen peroxide bleaching could be introduced. Hydrogen peroxide selectively oxidizes the residual lignin chromophores, which would further disrupt the lignin hemicellulose matrix. This is expected to result in more individualized cellulose fibers in SEM image and reduce the lignin-related peaks in the FTIR spectra. So FTIR spectroscopy was used to identify the functional groups and confirm the chemical structures of the accepted cellulose. So the bulk absorption bands around 3,241 cm per cube correspond to the OH stretching vibrations, indicating the extensive hydrogen bonding among the hydroxy groups, which is a characteristic feature of cellulose. The CH stretching bonds near the 2,900s confirm the polysaccharide backbone of the cellulose. A weak peak is observed around 1,555, is attributed to the carbonyl and aromatic structures from the residual lignin and the hemicellulose. The reduced intensity of the lignin-related peak occurs because the alkaline treatment saponifies the ester bonds and disrupt the aromatic lignin structures. However, without a bleaching step, some lignin and hemicellulose remain in the materials. The absorption bands around 1,422 indicates that the intentions of cellulose-1 crystalline structures, showing that the cellulose backbone is preserved during treatment. Strong peaks in the regions of the 1050 to 1017 together with the beta-1,4-glycosidic linkage peak around 878 further confirm the presence of the cellulose.
We present a comparison between the PVA starch composite film and cellulose extracted from cocoa pod husk. The table highlights the key difference in structural and functional properties, including mechanical strength, flexibility, hydrophilicity, and potential application. It shows that while both materials are biodegradable and sustainable, PVA starch offers better flexibility and film forming ability, whereas cellulose from cocoa pod husk exhibits higher rigidity and structural stability, making it suitable for reinforcement or filler application. Overall, this comparison helps in understanding how different natural and semi-synthetic polymer can be tailored for specific applications.
In conclusion, two different material systems were successfully studied, which are a PVA starch composite film and cellulose extracted from cocoa pod husk. The PVA starch film shows a smooth and compact morphology, indicating good compatibility between the polymer supported by strong hydrogen bonding observed in the FDR analysis. In contrast, the extracted cellulose exhibited a rough and fibrous structure due to alkaline treatment, with residual lignin remaining because no bleaching step was performed. Overall, this study demonstrates that polymer blending and agricultural waste valorization are effective approaches for developing sustainable and biodegradable materials.